A very good afternoon to our lecturer, Mr. Muhammad FARUQ bin Abdul Latif. My name is ZONG and my metric number is B09211048. Okay, today our group would like to present about the assignment, which is reducing the drag coefficient of AHMAD body using ANSYS FLUENT software. First, I would like to introduce about our assignment. First, we know that the efficiency and performance play a very important role in the car design. So we must understanding the principle of aerodynamics because it can minimize the drag, conserve fuel, and enhance the overall performance of the vehicle. For example, the AHMAD body serves as a fundamental model because it is closely resembles the set of the standard car. It also aids the engineer in comprehending the aerodynamic behavior of the car and their encounter with air resistance. Besides that, aerodynamic heavily relies on the drag coefficient. The drag coefficient demonstrates the level of air resistance that a car experiences. A lower drag coefficient has a lot of advantages such as it can reduce resistance, which can lead to improve the fuel efficiency, speed, and the stability of the vehicle. The ANSYS prover, which is a powerful computer tool that we had used in this assignment, is commonly used by engineers to simulate the airflow around vehicles such as the AHMAD body. It is a very useful computer tool because it can assist us in testing design modifications to minimize the drag without compromising the performance. Engineers must carefully design the shape of the car to minimize turbulence and reduce drag by paying particular attention to the rear of the vehicle. In addition, surfaces are made smoother and additional features such as spoilers or diffusers are incorporated to effectively manage the airflow. Method for controlling airflow around the vehicle exterior can effectively reduce the turbulence and minimize the coefficient drag. Next, I would like to talk about the objective of this assignment. First, the first objective is setting the performance baseline. We have conducted the CFD simulation to analyze the initial aerodynamic of the AHMAD body, such as the drag coefficient, flow pattern, and pressure distribution. Then we have identified the factor is affecting the drag coefficient by examining the CFD result to identify regions with significant drag. The next one is we must make modification to the design such as suggest the adjustment to AHMAD body geometry to minimize drag. We have made the adjustment to the rear air shape to ensure smooth surface, incorporate aerodynamic features, and so on. For the system, to conduct the systematically simulation, we have used the ANSYS FLUENT software to perform multiple simulations on the design. We also enhance the performance by using the optimization algorithm in ANSYS FLUENT to improve design choice. To ensure the accuracy of the result, we have compared the CFD result with experimental data of benchmark. After carrying out the assignment, we had to do the documentation and reporting to record the simulation workflow, including the setup, conditions, and setting. That's all from me. I would like to pass to my teammate, SHARUL IMAN.
Okay, thank you to Chong. Assalamualaikum to Cik Mak Faruq. My name is Muhammad HAIQAL bin MH.ZAINUDDIN. My matrix number is B09211048. Before continue the progress of this project, we do some literature review on the title given. First, by Zhang et al. On 2019. The title is Optimization Technique. This study focused on adjusting the rear slant angle and rear window angle to minimize drag coefficient. Results show a significant reduction in drag coefficient compared to the baseline configuration. Next, by Liang at 2018, the research about active flow control. What we find is through ANSYS flying simulation, they explore the influence of synthetic jet actuator placement on the flow, field, and drag coefficient. Their findings demonstrate that strategic placement of actuator could effectively manipulate flow, separation, and reduce drag. Okay, next for sent at 2020, the research is about surface modification. What we found is ANSYS FLUENT simulation were utilized to evaluate the effectiveness of rear spoilers with varying heights. The study concluded that properly designed rear spoilers could induce early flow separation, leading to a decrease in drag coefficient. And lastly, by Zhang at 2021, the title is about RES and LES simulations. ANSYS FLUENT is used to assess the accuracy and performance of Reynolds average, Navier-Stokes, and large eddy simulation in prediction, drag coefficient, and flow features. The study highlights the advantages of LES in capturing turbulent flow characteristics. Okay, for the procedure in our project, we develop using CATIA V5 software. As we can see at the screen, this is the dimension for the wind tunnel. With by using CATIA V5, the height is 1.356 meter and the length is 1.556 meter. So by extruding the design, we pad the shape of dimension 1.044 m times 7. So it can conclude the length of 7.308 meter. Next, I would like to give to others member Chan.
Hello to Engineer FARUQ. My name is Chan Deha, lecture number 092110146. Now I'm going to explain about the procedure of armor body. So we click on the surface of the structure build stunner and we draw a wind armor body inside of the surface with the dimension given on the first page. Then we make a hole at the armor body about 0.195 meters, and then we next front page. That's it. So we create a chamfer at the behind of the armor body and fillet the armor body by clicking on three surface of the edge. Next. Then we save the file as the STB file. Next. So we open the ANSYS software we import the geometry of the STP file inside the ANSYS. So we choose the solution of engineering solution, choose CFD, accuse so, and we click OK. So we need to scale down the geometry by clicking on the XYZ scale 1000 and then click on scale down. Then we click on component parts like body, symmetry, wall, and then floor. So we click on organize on each part. We choose a surface that related to each. So then we delete the part. So we show that the shape will be different colors. Next. Then click on the auto mesh. So we click on the surface deviation. For the minimum size, we choose 0.01 meter and the maximum element size of 0.032 meter. So we click on surface, we choose offset the AHMED body, the body. So we click mesh. For the AHMED body, we choose surface and bias with the element size of 0.01 meter and click mesh. Next. For the tetra mesh, CFD tetra mesh, we click on the boundary selection. We choose simple select and smooth truncate boundary layer. So for the BL fix, we choose component body and floor only. While without BL fluid, choose the rest component beside of the body and floor. So for the BL parameter, the setup is default and does not need to change any value. Then click mesh. So it will come up the CFD tetracore and the CFD 001. So this step we need to merge the tetracore to the CFD 001. So we make the CFD 001 as the macaron and then organize. We choose CFD tetracore to merge inside the CFD 001. And next. Then we delete the CFD tetracore. After that, we save the file as a cast file. The file is the FLUENT file. Then next. So import to the ANSYS. We open the drag the FLUENT tools into ANSYS. So we import the geometry of cast file into the ANSYS. We click edit on the setup. Next. So at the setup, we click on a resource. We select the palette almas for the resource type. Next. So we're setting the inlet and outlet pressure. So inlet, we can see in the picture the area of 0.065740099 meters square and the length of 1.044. Next. Next, we click on the hybrid initialization and click calculate initialize. Next. After all of this step, then we click on run calculation. The number of iteration is about 1000 and then we click calculate. So next, pass to the next person.
Hello, my name is SHARUL. My metric number is 09211028. So this is the post-processing after using the simulation. So the first thing we have the conjugate. there is the first set is the pressure, the high end and low end. At the high end, it got 120, and at low, he get 193. Next. Next. And this is the velocity of the wind tunnel. We got 90.93 meter per second and 0 at the boundary layer in the AHMAD body. So next. This is the calculation using spiral Almadas, velocity, continuity, in, out, and x velocity. Next. This is the drag coefficient. For the drag, we got 0.3, 0.336, something like that. Next. For discussion, I pass to Yumni.
Okay, so my name is RUZAINI bin Ahmad. I would like to explain about the discussion of all these assignment. First of all, the AHMED body is simplified automobile model used in aerodynamic research to better understand the effect of form on drag and flow characteristic. Then improving fuel efficiency and performance in car design requires reducing the drag coefficient, which means the CD. Then the ANSYS FLUENT computational fluid dynamics, which is CFD tool, is commonly used to stimulate and analyze airflow around such bodies to find and execute design change that reduce drag. Then to minimize the drag coefficient of an AHMED body with ANSYS FLUENT, first create the AHMED body model geometry and mesh it with a small mesh near and the body and cursor mesh farther away. Next. Then define boundary condition with a velocity inlet, pressure outlet, and no slip wall conditions. Choose the K omega SST turbulence model for better accuracy and run steady state simulation to observe airflow. Then compare the drag coefficient of each improved design to the baseline model and ultralight flow visualization to see the impact of modification. Lastly, this improvement can dramatically lower the drag coefficient, hence improving vehicle performance and fuel efficiency. Okay, so the conclusion of all the project, using ANSYS FLUENT, you may reduce the drag coefficient of an AHMED body by simulating various design adjustments and examining their influence on airflow characteristics. The rear slant angle should be optimized, vortex generators added, the underbody modified, and edge rounded. The data gathered by this model are used to build more aerodynamically efficient automobiles, eventually enhancing performance and fuel economy. Okay, so that's all from me. Thank you.